Hey there, Math 2403. Welcome to Unit 4. I'll just have one long video for this unit on continuous probability distributions. We'll discuss only two specific distributions, the uniform probability distribution and the normal and standard normal distribution. In the intro to this, I will discuss a little bit of calculus just for those people that are interested in how we actually find the probability by finding the area beneath curves. So if you have some background with calculus 2, then that stuff will seem familiar. If you don't have background in calculus, it's okay, just follow along. You're not required to know any calculus. I just put it in there for completeness and to show off. So let's get right to it. Continuous probability distributions. And we'll see that we've already been doing probability distributions in the discrete case. And in the discrete case, we had basically, we listed all the possible outcomes of an experiment, and then each one had an associated probability, and the probability of each event could be expressed as the area of a rectangle. And we were, with the binomial distribution and Poisson, etc., we were like summing up rectangles to determine the area beneath the curve. Now, when we move to the continuous case, instead of summing up rectangles, we all know that adding up an infinite number of rectangles is essentially the process of integration, where we have, the fundamental theorem of calculus aiding us in determining probability. When we have our curves, they'll have to be special curves. They'll have to have, the feature that the total area beneath the curve is still 1. So that's this expression here. If this function is f of x, if we integrate the whole thing from, the left endpoint to the right endpoint, in this case, maybe minus infinity to plus infinity, the total area has to equal 1. The curve has to always be above the x-axis. That's the next condition of the probability distribution. And we will look for the area beneath the curve. We can look at various intervals, look between A and B and determine, say, that area. So all of our previous training, learning how to integrate, pays off here, because we can now find, we have a new application where we're finding probabilities. And all of these probabilities have to be less than, like the area that I've drawn here between A and B certainly can't exceed 1 if the entire area beneath the curve is a total of 1. And that's what this little, condition is saying. We remember the fundamental theorem of calculus, where if we define the function as little f, the area beneath the curve, or the antiderivative, is then described as capital F. So we can use this notation. Capital F of x is the area beneath the curve up to point x. So you'll have some curve defined by f of t, t-axis here, and then at some point x, we'll find the area up to that point using this integral. That's the cumulative probability, like we were doing with the binomial, where we were adding up a bunch of rectangles up to some point. We tried to convert our problems into less than or equal to problems, because that's the way our tables worked. In this case, this is the way most software works. It finds the area to the left in a cumulative way. The fundamental theorem of calculus, then, we all know that we can just find the antiderivative of little f, that's big F, and if you're on an interval, you just plug in the endpoints. So if you're integrating from a to b, it's the antiderivative evaluated at b minus the antiderivative evaluated at a. And here's the relationship between the two functions. If you take the derivative of big F, you get back to little f. Hopefully that stuff is familiar, hopefully not too scary. When we had these distributions for the discrete case, we found the mean and standard deviation. We can do the same for the continuous case. In the discrete case, for example, the mean was the sum of each outcome times the probability of that outcome. And we added those all up. You know, there was we had a finite sum, but in the continuous case, we'll be adding up an infinite number of areas. So, you know, we just basically stretch out that summation notation and write it as that traditional integral notation. So the formula is pretty much the same. We're just going from the discrete case to the continuous case, from, you know, a fixed set of rectangles to an infinite number of rectangles. And the variance is the same formula too. It's that weighted distance away from the mean. And now we're just doing an infinite sum instead of finite sum. We can do an example here. One common continuous distribution is the uniform probability distribution. I have an example here. It's a little bit fake, I guess. It says we have some light bulbs and they all last between 0 and 3 years. So I'm going to try to draw a little picture here, you know, 1 year, 2 year, 3 year, and I'm trying to model the life of these light bulbs. And it says that their probability to fail is equally likely at any time during the 3 years. So during that time period, at any given time, they're equally likely to fail. So this is a uniform distribution in that that probability never changes. At any point, it's the same. Here's the part that isn't exactly realistic. They all last between 0 and 3 years. So there's nothing beyond 3 and there's nothing before 0. This is our entire sample space. So the area beneath this curve that we've drawn has to equal 100%. And because it's a rectangle and the base of the thing, you know, has length equal to 3, the height must be 1/3 so that the total area equals 1. You know, 3 times 1/3 equals 1. So that's our function. You know, f of t is 1/3. You know, this is our t-axis. This is our f of t axis. And then if we wanted to find, you know, probabilities underneath that curve, you know, we could say f at some value x is the integral. In this case, the lower bound is going to be 0, and we'll integrate up to x, our function. In this case, our function is just 1/3. So it's an easy integral. This function here will give us the area up to some point x. So say I mark some spot x here. I can get the area beneath the curve up to that point using that integral. Of course, the geometry here is so easy that we probably wouldn't need to do any integrals for the, you know, continuous or the uniform distribution, because we're just looking at, you know, rectangles. So we're just finding the area of rectangles. We probably don't need this high-powered math, but I'm just showing you that this is how you do it in the simple case, and it would apply to any shape. The area that I've shaded is big F of x. So the question then is, what's the probability of randomly picking a light bulb that lasts up to 2 years. So we want the area under the curve up to 2 years. I think we can probably see that the answer there is going to be 2/3. It's this distance times that distance, so 2 times a third is 2/3. Or we could integrate it. We could say f of 2 is the probability that x is less than or equal to 2 which is then the integral from 0 up to 2 of 1/3 dt. So we'd get 1/3 t evaluated from 0 to 2. So it's 1/3 times 2 minus 1/3 times 0, fundamental theorem, and we get 2/3. Of course, we didn't need to do all that work. I'm just showing you that that's how you would do it for a more complicated curve. You'd figure out the equation of the distribution, and then you integrate to get the probabilities. Find the probability of randomly picking one that lasts between a half a year and 2 years. Now draw a little picture here so you can see what we're doing. We want a value between a half a year and 2 years. So we're looking for this region. In this case, it looks like, and it will be, exactly half of the area. Of course, you could integrate it if you'd like. You could say it's the integral from 1/2 up to 2 of 1/3 dt, which is then 1/3 t between a half and 2. And then I guess we could factor the 1/3 out and say it's 2 minus a half, just plugging in the limits of integration there. And of course, we get 1/2. When we're doing these problems, we see that the word between is tricky. When we had the word between in the discrete distribution, if I said between 5 and 7 of you are going to fail this course, does that mean 6 people are going to fail the course? Or does it include the 5 and the 7? In the discrete case, it really matters what that definition of between means. In the continuous case, it doesn't matter, because including the endpoint or not including the endpoint doesn't really matter. You're not getting any extra area. It's an infinitely thin line at each endpoint. So whether you write these things with less than or equal to or strictly less than in this example, you'd still get the same result. So we actually get to be more relaxed about the definition of between. Same with less than versus less than or equal to, more than, greater than. With all those definitions in the discrete problems, we had to be very careful about how we interpreted those. But in the continuous case, it doesn't matter, because there's no area at any one point. And that's demonstrated here. Find the probability that we randomly pick a light bulb that's going to last exactly 1 year. Well, on that continuous time frame, we're trying to pick 1 year. How much area is there beneath the curve right at that one spot? And the answer is nothing. It's it seems weird that it's impossible to pick one that lasts exactly 1 year because there's an infinite number of possibilities between 0 and 3 years. So how do you pick any individual when you have an infinite number to pick from? So there's one success out of an infinite number of choices, which then makes it impossible. So yeah, the exact problems are now all 0. In the discrete case, we were able to solve exact problems because that was just one rectangle that we would find the area of. We could maybe define 1 year as I can only measure it. I'm limited by my measuring device. Maybe I can only measure years to 2 decimal places. If that's the case, then 1 year is technically, 0.995 up to 1.005. And I could find the area underneath the curve on that tiny range. But you'll still get something pretty small, even if you're talking within the practical limits of your measuring device. We've seen this bell curve throughout the course. Even the first lab, I believe you plotted this thing. The function for the bell curve is rather ugly. It's an exponential function that has a couple parameters in there. It depends on mu and sigma. Its shape varies depending on mu and sigma. Finding the area beneath this curve is hard. In fact, it turns out that this function isn't integrable. It has no antiderivative. It's weird that the most fundamental function in statistics, perhaps, is something we can't integrate. So we always have to do numerical approximations to get area beneath the normal curve. That might involve Simpson's rule or, one of the other numerical techniques that we use for integration. Of course, we can basically get it as precise as we want by, just doing more steps in our numerical approximation. When we're looking at this curve, you'll see I plotted a few different versions of the normal distribution. You'll see sometimes it's skinny, sometimes it's kind of flat. And that all depends on what our values are for mu and sigma. This is what we always draw. This typical shape is what we have in our mind for a bell curve, but they're not all like that. Some are narrower, some are wider. In this case, the green curve here has a mean of 0 and a standard deviation equals 1. That's called the standard normal distribution. Then if I make the standard deviation smaller than 1, it means it's not as spread out, and that's when I get this red curve. I still have to have a total area equaling 1, which is why, I have to keep adjusting that thing. If I have a standard deviation larger than 1, then it starts to look like the blue curve. If I change the mean, it just shifts it left and right. So this magenta curve here is, I changed the mean to be -2. So we have a lot of normal distributions. And each one of these then, we'd have to calculate the area under the green one sometimes, under the magenta one other times, under the red one other times, and they all require numerical integration, which is rather painful. So what we need to do is come up with a better way, I guess, where we can transform these guys. Basically, we can find the area under the green one, the standard normal, all the time, even if we are dealing with a magenta curve or a red curve, by doing a transformation. And that transformation involves z-scores again. So z-scores come back to haunt us. Remember, z is x minus mu over sigma, or it's x minus x bar over s if you have a sample. It turns out that suppose you have a data set and you calculate the z-score for each value in that set. So you have a new data set, a set of z-scores. When you find the mean of the z-scores, the mean always ends up being 0. Some of the values are above the mean, some of the values are below the mean, and the whole thing balances out. And you end up getting the mean of your z-scores is always 0. An even cooler property is that the standard deviation always ends up being 1. So that's why we use this standard normal distribution so often, is that the mean of the z-scores is always 0, and the standard deviation of the z-scores is always 1. So that allows us to transform any data set, regardless of its mean and standard deviation, into a z distribution, assuming that the original data came from a bell curve itself. I shouldn't say just do it for anything. So let's take a look at this a little further. We already know the area beneath the curve a little bit from the empirical rule. Remember the 68, 95, 99.7. If you are between -1 and +1 in your z-axis, remember that this area was 68%. So we've already been talking about the area beneath the curve, and now we could actually get this percentage. We could take our function here and integrate that thing between -1 and +1, and we would then generate this 68%. It would be hard because we'd have to do numeric techniques. So a table's been devised that gives the area beneath that standard normal curve. So if you know your mean is 0 and your standard deviation is 1, this table will give you the area beneath the curve. It's cumulative. It's the area up to some point z. So if I want the probability that z is, say, less than 1, maybe I'll write, how about we do 1.00? That's the spot here, and we're looking for this area. On the table, I find the number 1, and it's 1.0, and then the next decimal place is a 0. So that area ends up being 0.8413. If I want the probability to the left of, 0.54, I go to 0.5, and the next digit was a 4. So that's how you read this table. It gives you 2 decimal places for your z-scores. That one's 0.7054. The table only goes to the left. So if you have problems that are to the right, then you do 1 minus, use the complement. Notice in the second case I use less than or equal to, and in the first case I use less than, and I didn't change my technique. The area is still the same. So sure, that's important maybe from the question that you're solving, but it actually isn't important in reading of the table because the area is the same. So we'll use this table a lot. In your formula packet, you'll also have the table for the negative z-scores. Although you can always do these problems using symmetry. You don't really need a negative z table. Here's a quick example. I tried to dream up an example of a real-world situation where you would have a mean of 0 and a standard deviation equal to 1. And I took a little while to dream something up, but I figured that we could test cheap thermometers. Suppose we manufacture cheap thermometers, and At one point, we test them. We dip them in freezing water and we read them. And usually our thermometers read the freezing point to be 0, but they're not perfect. They're cheap. So sometimes they read a little high, sometimes they read a little low, and we get a standard deviation of 1. I used mu and sigma here because I've been manufacturing these thermometers for years and years, and I have so much data that I feel confident I can use population parameters rather than sample statistics. Now, I reach into a box of these thermometers, and I haven't tested it yet. What are the chances that it will show me that the freezing point is somewhere between 0 and 1.35? I used my variable z there because this is a special situation where we have a mean of 0 and a standard deviation of 1. So my data is already in terms of z-scores. I'm looking between 0 and 1.35. Again, I could have written strictly less thans here and I get the same result. On the z-curve, 0 is in the middle. The average distance away, or how far away is the mean from the mean? 0 standard deviations. And 1.35 is up here someplace. And we're looking for this area. I strongly recommend you draw these little pictures. They make your life easier, and you'll tend to not get these wrong if you can see what you're actually trying to solve. So we just need to find this area. Now the table gives me the area going to the left. Like, I can easily get less than or equal to 1.35. But I don't want the whole area to the left of 1.35. I just want the area between these two values. So basically my strategy here will be, find the area to the left of 1.35. I can get that from my Z table. And then take away the part I don't need, which is the area to the left of 0. So that's how we'll solve these. In this case, I guess technically I probably should write, to be accurate, I should go less than 0. If I want between 0 and 1.35 and I included the 0, I don't want to take 0 away, although it doesn't matter. So let's look up 1.35 back in that table. Let's erase some of these scribbles. We go to 1.3, and our next decimal place was 5. So we get 9115 is the area to the left of that. So this area is 0.9115. This area to the left of 0, I don't even have to go and look that one up. It must be 0.5. It's half of it. So 0.9115 minus 0.5000 is 0.4115. And we've done it. There's a 41% chance that if I randomly pick a thermometer out of the bin, that if I dunk it in cold water, that it will read the freezing point to be between 0 and 1.35. Maybe more interesting way to answer that would be to say, 41% of my thermometers are going to read the freezing point between 0 and 1.35. What's the probability of getting one that will read exactly 1? And the answer is, it's impossible. There's an infinite number of choices. The next example, how about between negative 1.35 and 0? So one that's below freezing. Certainly, because of symmetry, I think we can answer it without even needing another table. If we know this area, it has to equal that area, although you can't tell by my drawing. And we already did that one. It was 0.4115. Of course, if we hadn't already done the previous one, that's what we would do. We would just write this is equivalent to this, and then look this one up in our table to get our answer. So take advantage of symmetry when you can. Again, what's the probability of choosing one that's between negative 1.35 degrees Celsius and positive 1.35 degrees? Well, it's just double the other one. So 2 times 0.4115, which is 0.8230. We're really doing a lot of examples here. The reason for this is we use this normal distribution over and over throughout the course. So we really have to make sure we have this thing rock solid. We hate to get a question wrong later by making a little mistake because we didn't know how to read the table yet. A greater than problem. The table doesn't do greater than problems. We're looking for, a thermometer that thinks that the freezing point is above 1.35. We can do 100% minus the probability that we're less than or equal to 1.35, which we already looked up. That was a 9,115. So then we have 0.0885. Roughly 9% of our thermometers read the freezing point as 1.35 or higher. And then the hard question, I guess, is find the 75th percentile. So, which is a good question because it kind of, reminds us of something that we had done before. Somewhere on this axis is the 75th percentile. I'll put it here. The area to the left of that then is 0.75. And we want to know the number that goes with that. So basically, we know the probability and we want the z-score. So going back to our z table, I'm not going to, this is not what I want. That's not the 75th percentile. What I want to do is search around in the probabilities for the number 75. So I'm looking, and luckily they're in order, so it's not too hard to find. It's somewhere between these two. I don't think we should bother interpolating. In fact, linear interpolation might be a bad idea, on a curve like this. So maybe we'll just be conservative like we did when we were doing percentiles in the past. We always tried to err on the high side. So let's err on the high side. Let's use the bigger one. What value is associated with that? 0.68. So the spot on the x-axis that goes with 75% is 0.68. P75 in this case is 0.68. And this one has units because our original data had units. Usually z-scores don't have units, but this one was, carefully rigged so that the data equaled its z-score, and therefore we still have units here. So that's not too bad. Hopefully you can read that table. If you're more of an Excel type person, I did this example with Excel. The formula that we use is called norm.s.dist. The S is for standard normal. So norm.s. The parameters that you input are the z-score and whether or not you want it to be cumulative. So it's similar to when we did the binomial and Poisson. To find the area to the left of a particular value z, we use this formula with a 1 for cumulative. In fact, we're never going to put a 0 for the cumulative flag in a continuous distribution because that is an area of 0 anyway. What Excel outputs when you put a 0 in for the cumulative is actually the curve. So putting in 0 here would allow you to plot the z curve. So it doesn't actually give you probability. So always put a 1 for cumulative in your calculations and you'll be happy. The example we just did, we did the area between 0 and 1.35, and we broke it down into 1.35 minus the probability to the left of 0, and we have to do the same thing in Excel. Like, we still have to set up the problems. Again, this is why I recommend drawing the little pictures, even when you're using Excel. So in this case, I want norm.s.dist, the area to the left of 1.35 minus the area to the left of 0. Of course, I could have just hard-coded 0.5 here. Exactly 0 is the next example we did, and I just typed 0 here. Don't use the function. It doesn't return the correct answer. Use this function only for cumulative things. The next one we did was negative 1.35 up to 0. When we did it by hand, we just cheated and stole this using symmetry, but we certainly could go to the left of 0 minus to the left of negative 1.35. To the left of 0 is a half, and then to the left of negative 1.35. The function accepts negative values. So we can just go through all of these in the same way that we were doing them and using the table. And it's pretty fast. To do the inverse, the 75th percentile, we use dist to get probabilities, and we'll go inverse to get values. So it's norm.s.inverse, and all you have to input there is the probability. So I input 75%, and it gives me the z-score. So it's pretty easy to do in Excel. In fact, I recommend doing them this way. Another example here. I said we're kind of, really going after these things to make sure we get this. if you're listening to this video, hopefully you're doing it on at least 1.5 speed, because we're kind of doing the same thing over and over again. Here's an example where we're looking at 3-inch nails. They aren't all 3 inches. On average, they're 3 inches, but there's quite a bit of standard deviation, 0.1 inch. So it's similar to the thermometer example, except now we don't have a mean of 0 and a standard deviation of 1. We basically have to do a transformation. Remember, to transform a value to z, it's x minus mu over sigma. And that's basically what we're going to do here. We'll have our nails, and they have some length x. So x is length in inches, and we're looking for what's the probability of picking one that's between 3 inches, which is the mean, and 3.25 inches. I want this area. I'm just trying to get a rough sketch of this thing. I'm not exactly sure how far away I need to write it from 3. In fact, I probably should have drawn it a little bit further to the right because the standard deviation is pretty small. 3.25 is a couple of standard deviations away. So I'm already getting, into the tail. But I just want to have a rough idea of, what direction things are in. What we're going to do now is convert these x values into their corresponding z-scores. So to write this out, we'll say we want a nail between 3 and 3.25, and then we'll convert these to their z-scores using this transformation. So 3 minus 3 over 0.1 is less than z, is less than 3.25 minus 3 over 0.1. So we get the probability of having a z-score that's between 0 and 2.5. Now we can find the area under the z distribution between 0 and, I probably should have drawn it a little further out, 2.5. At least I'm consistently inconsistent, or I'm consistently wrong here. This area is going to be pretty big. It's going to be further into the tail than I've illustrated, I think. Because 2.5 standard deviations above the mean is pretty far away from the mean. Remember when we talked about the empirical rule, 2 standard deviations away gave us a total of 95%, and 3 standard deviations was 99.7%. So we're between that 95 and 99.7 range. So I think we should be further up, but you get the idea, hopefully. When I dove into this problem, I probably should have mentioned, I'm looking back at this, what gave me the right to just start drawing bell curves? Well, they told me it was normally distributed. So I better, be aware of that. If it said this follows a gamma distribution, well, then the shape of the curve is different, and then we'd have to find the area beneath the gamma curve instead of the normal curve. So for now, we only know the normal distribution and uniform, so it's pretty easy to decide what to do. But we will learn many others, actually, just like we did for the discrete case. To solve this sort of problem now, we did this where we went less than or equal to 2.5, and then we take away the probability of being under 0. To get this area between 0 and 2.5, I find the total area to the left of 2.5 and take away the part I don't want. going to our trusty Z table. Actually, I have a tab here with tables. How about we go to the trusty normal table? Looks like it's already been used heavily. Let's see if we can find 2.5 on here. 2.5, and we had the next decimal place was 0, so that puts us in the first column. So our probability is 9938, so 0.9938. We can jump back over to our problem here. This area here is not 9938. It was just this piece of it. We're taking away this piece, which is 50% of it. So our answer is 4938. 49% of our nails have a length between 3 and 3.25 inches. We can go on and do other examples. What's the probability of getting a long nail longer than 3 1/4 inches? Do the transformation. 3.25 minus the mean was 0, standard deviation 0.1. We've already done this. Z is greater than 2.5. So again, if we were to draw the two pictures, we have our X scale. 3 was the mean, 3.25 was, say, here. We want the area to the right of it. We do the transformation to Z. It has 0 in the middle. Our Z score is 2.50, and the area to the right of that corresponds with the area to the right of 3.25 up above. We have units in our original data. Z scores don't. Greater than problems can be solved using the complement. And we already looked up 2.5 in our table. It was 0.9938. And then we get a final answer of 0.62. 0.62%. It actually asked for percentage here in this question. So I guess it was right of me to convert that to percent rather than just leave it as a decimal. We're getting close to the end of this one. We want the probability now of getting one that's too short. What's the probability of having an X that is less than 2.75 inches? So 2 3/4 inches. Calculated Z score. .75 minus the mean of 3 and the standard deviation of 0.1. Remember, we have our Z score formula. That's how we do the transformation. So we get a Z score of, what do we get? Negative 2.5 there? Yeah. So if we were to draw this thing out, here's X, the mean is 3, we're looking at 2.75. We want the area to the left of it, so we know we're looking for a small value. We did the transformation to Z. We got negative 2.5. And sadly, I don't have a negative Z table on me, so I'm going to have to use symmetry. You'd probably agree that that's the same as the area to the right of positive 2.75. So I can write this. Z is greater than 2.75. Notice I didn't have to do 1 minus here. I was just simply using symmetry. I wasn't actually doing the complement here yet, but I think I need to do it now because now I have a greater than problem. Now, if I want this little area here, I guess I could do 100% minus the area to the left. Oh, I changed my number here. This was 2.5. Sorry. And I even wrote it wrong here on the z-axis. This is still 2.8. I said you would agree with me that this equals. No, you wouldn't. But maybe now you would. Good. Now you know that I don't edit the videos. Now we already looked up the area to the left of 2.5 in our Z table. Oh, look at that. It was 0.9938, which is 0.0062, which is 0.62%. I mean, you probably could have seen that just by looking at the previous example, that that's what we were going to get. But I wanted to show you, this whole idea of, using the positive table to solve a negative problem by taking advantage of symmetry. Later, we're going to learn, a few other distributions, and rather than flood you with positive and negative tables for all of them, we typically just give out a positive table and then you take advantage of symmetry to calculate these probabilities. Another example. I think we have 2 to go. Hang in there. If a nail is shorter than 2.75, it's no good. If it's longer than 3.25, it's no good. What percentage of these nails are no good? Well, I guess we found that. We found the percentage that were too short, and we found the percentage that were too long. The probability was 0.062 and, times 2. 0.0124 or 1.24%. 1.24% of our product is, outside of whatever specification we have. And then finally, the percentile question, when you don't have a standard normal distribution. I want to know the 95th percentile for my nail data. I just start out by sketching the thing. They told me it's a normal distribution. X is the length of a nail. 3 was the mean. We're looking for some value up here, P95. The area to the left of that, whatever that spot is 0.95. So basically, we're working this problem backwards. I'm going to figure out the z-score that corresponds with that. What z value? I'll put maybe Z95. Sounds like a radio station. If I can figure out the z-score that goes with 0.95, an area of 0.95, then I can hopefully figure out what x goes with that. So back to our Z table, I want to look in the table for 0.95. So I need to read the table backwards again. I don't want to look here. That's a Z-score of 0.95. I'm looking for an area of 0.95. So I'm searching through the table, looking for 95%, and I'm finding it, right there. So it's exactly halfway between these two. I could be conservative and say 1.65, choose this column, and that would be a good choice. But it turns out that the interpolation works. It's actually right in the middle of those two. That value gets used often, so it ends up being on our table. We get one extra decimal place of precision there. We can actually call this 1.645. Of course, I wouldn't hold it against you if you used 1.65 and erred on the high side. But let's use the value as long as we have it. This z-score is 1.645. Maybe put a little note here. Read table backwards. Because when you look at your notes, it's hard to see what happened in this question. This number just appears. Even in the video, it might seem weird, especially if you're watching at 3 times speed. The conversion between z and x is z is x minus mu over sigma. We know that 1.645 corresponds with the 95th percentile. And we know the mean and standard deviation. The mean is 3, and the standard deviation is 0.1. So solve this equation, and you get the 95th percentile is 3.16 inches. "95% of our nails are 3.16 inches or less." 95% of our 3-inch nails are 3.16 inches or less. I think that's a good place to end this video. So I hope you all have a good one, and I will see you next time.